left, right. Okay, let me just skip that. I changed it a little bit because I'm going to introduce what research informatics is. If you look around here, sorry, and I made a stupid joke previously and did it myself. So if you look around here and you see people with a blue lanyard, and they have a scrubby beard, most of them are in the development team. But the development team is not the only group that works on introducing new technology. There's also the research informatics team that aims to develop solutions to problems that we currently don't cover in our software. And so these are the people right now who work in the research informatics group. So mostly Alex and I have been around for quite a while. So Alex is moving back there. And then there were a few people who used to work in the team. Some of them are still with us in CDD. So various of the technology that we developed made it into the product. Barry already mentioned one-click models. There's also the whole area of assay informatics, which came out of a different product that we had. It's called BioAssay Express. Actually, I just skip on because I cover all of these anyway. So assay informatics is, if you work in a company long enough, you are suddenly facing, I mean, there was one project that had 77 assays. Now, think about a larger company that has maybe 10,000 assays, and you don't know what they are. Usually, sometimes they just have a name, one name, and that's completely non-descriptive. And your hit comes up and it's active. So what do you do? In order to have assays, they need to be properly annotated. And that's what we tried to solve with the assay informatics that we developed. And basically because that would then allow you to search assays by, first of all, get the information, but then also search assays more effectively. And so currently, we have that integrated into Vault with the assay protocol and protocol annotations. So there was an older implementation that we kind of phase out now because it's now part of where you define your assay protocol. So you annotate them with ontology terms, and that gives you a defined vocabulary, and that helps you then identify better what the assay is actually doing. We also introduced mixtures into CDD Vault because in real world chemistry is always very often mixtures. If you run an assay, it's not just the compound in there, it's also a buffer. And sometimes, you need to know what is in there in order to identify maybe side effects of components and so on. So it's part of the standard CDD Vault. And they're part like an entity, and you can do search them and so on. Another technology that we developed is what we call SuperSAR. That's part of visualization. In SuperSAR, we take our chemical space and we fragment it and organize it, and that allows us to faster navigate the structural space. It shows up in these fragments, and it allows you very quickly to say, okay, instead of defining a substructure search, you just click it and you see what compounds match the fragment. We also use it to more easily select cores for the R group analysis. So if you haven't really tried it out, give that a try. We also contributed to the change of the CDD chemistry engine that we introduced last year, which is based on RDKit. And I should probably put a TED on that as well, because TED did the atrope isomers. So should take that off the slides here. But basically, our contributions go back into RDKit, which helps the community in a larger area. The advantage of having our own chemistry engine is that we can more easily react to customer queries. But now I continue to what Jeff already set the scenes. Of course, we also try to have a look into deep learning technologies. And I don't like to use the term AI because it's kind of similar to what we've done 30 years ago with just standard fingerprints and so on. So the model that we trained is I guess this one, yeah. Is a graph convolutional network that creates a numerical representation, which is unique for the structure. So it doesn't really matter how you define your structure and in which order your atoms are. But then we couple the latent vector with a generative model, which is, in this case, it's a SMICE to SMICE generator. And the disadvantage of having SMICE is they are atom order dependent. So that isn't necessarily a good approach to do QSAR models. But this side here, as we've heard, gives you a good description of the chemical space. I think the way we trained this helped us to organize the latent vector space in a way that that we can show that it covers structural information. So what we see is that if we take a chemical structure and it doesn't really matter what it is, if you then add a specific functional group, it always shifts the latent vector in a certain direction. So if you are aware, if you have come across some information about word embeddings, they observed similar concepts, like going from man to woman in a word embedding is similar to going from king to queen. So we could show that that works as well here. We also can show that similar structures are giving similar latent vectors. And now, of course, the question is how can we embed this technology into CDD Vault in a way that is easy to use, that it is also not over-promising. And so I show you now how we actually did, what the various ways we tried to approach this. So when we evaluated our system, we can show that the latent space encodes structural information, and similar structures get a similar numerical representation. So we can use it to do similarity searches. And the way we embedded with this so far is to have a latent vector database, a database of Campbell compounds, and you can access that from the molecule page using this link here, find Campbell compounds using deep learning to similarity. It then searches through Campbell in a secure way, so your structure doesn't go out to Campbell, it's done internally, and then you get similar structures here. So you can then click, I mean, at that point, these are known structures, so you can click on the link, you can go out to Campbell, you can learn more about your structures. We are working on integrating Campbell to have patent information as an additional way of assessing your IP if you have a novel hit. Potentially, we also look into integrating some commercially available screening libraries. Another thing that we identified when we analyzed our system was that we can break down the numerical representation of a structure to individual fragments of the structure. So we can get the numerical representation of the phenyl group, of the carboxylic acid group. And again, can use that and we see that phenyl groups in general have similar representation, carboxylic acids have similar representations. And so we integrate that in a system where we take structures, we chop them apart using a retrosynthesis-based approach that goes back to early 2000s. And then look for fragments that are potential replacements for in an existing structure. Utilize this retrosynthetic knowledge to make reasonable suggestions. And we also use the Payne's filters by Jonathan Bale and other structural alerts to avoid that we introduce novel additional structural alerts. If your structure already has structural alerts, you're on your own. This is how we integrate it, and it will come to CDD Vault soon, or it's actually almost, well, it's almost there. Again, it's accessible from the molecule page. You click then this link here, suggest by isostairs, and you can see what you basically get. So in this case, it replaces this 5-ring structure, and there are a few suggestions here. I'm pretty sure some of you will say, oh, you should never make that compound, but there are ways we can tweak that and work on that. We can also show the calculated properties. That's relatively small here, but let's say this is the molecular weight, the log P, and the CNS MPO. And I got my warning, okay. I only have 3 more slides.
I'm glad it works.
So all of that is available in the standard user interface. We have additional functionality that we only make available currently through an API. So that's probably more for the people who are more technically aware, like computational chemists. So we can use that. You can upload an SAR data set and build QSAR models. And as Jeff mentioned, graph convolution network creates the features, and then we use an XGBoost model to build the model. And we were able to show that this gives us models which are, in general, as good as standard models. We work on having a bit kind of incorporating multiple models, multiple assays that are part of a project, and then you could optimize your structures in that. And this is now where it gets more speculative, because now if you have a structure and you know, oh, I have to modify, I increase activity or I improve log P values if I go in a certain direction, then you are, of course, suddenly in a point in latent space where you don't know what the structure is. You could either search a database, or you could we could feed it into our generative model and then create candidate structures. That is more speculative, and having worked as a computational chemist in the industry, you only have a couple opportunities to suggest something to a chemist that it will not be active. So you won't. Don't use that. Final one, we also looked into mapping that vector, which is a high-dimensional vector, down to a 2D representation, so we could then represent our SAR dataset in a little map. For smaller SAR dataset, that's relatively feasible, and then you can visualize it. And that gets me to the end. Are there any questions?
Are there any questions? Go ahead, Jeff.
So you mentioned that there's many problems trying to train models to
We tried that to also then train the generative model. We didn't really explore this in depth, but we didn't see any advantage compared to SMILES. Yeah. I mean, I would like to, it's a GRU model, and I would like to try transformer models, of course, nowadays, because that's the better technology now, or one of the other, like Mamba. So.
Thank you, Jeff. Any questions? Okay. Thank you, Peter.
Thank you.